Hello, everybody. I'd like to welcome you to the new edition of Investigation Bible. I'm your host, Bill Kaufman. I'm now 10/8 on this shift for this episode. We're on duty. All right. Um, Last week we spoke about some scientists. We spoke about the people that were foundational in science and all that kind of stuff. Guys from the Renaissance and from the Enlightenment eras. So, we did speak on different people like Newton, and I believe we brought up Descartes and things like that. Da Vinci. Different people lived in the 14, 15, 1600s and stuff. That's who we spoke on last week. Now, this week, we're going to continue talking about some science stuff, but not so much just individuals. That's not what we're going to be going for. We're going to go for a topic called thermodynamics. And why am I going to talk about thermodynamics? And why does that even matter? Well, we'll get to that by the end, but I think you'll see how it relates to the Bible and what the Bible teaches, okay? And what the Bible would teach us to expect science to find out eventually. And they did a long time ago now, but the Bible was written a long time before that. All right, so we did speak on Newton last week. Isaac Newton, everybody knows him. The History Channel at the turn of the last eon here, last century, at 2000, they came up with the top 100 people that were most influential over the last 1,000 years. And number one, they came up with, in their estimation, was this guy, Isaac Newton. I believe number two was Martin Luther, and three was Einstein. And I could be wrong. I'm just going off memory. That was 20 something years ago. But think they're getting a lot of arguments for Isaac Newton being that important because he was that important. All right, but he wasn't alone. He lived in a time where a lot of people were thinking, amazing thinkers lived, I should say. I did just bring up Descartes. Rene Descartes, he was French. Now, he did most of all his stuff in the Netherlands because of what was going on politically with the Catholic Church at the time. He lived at the same time as Galileo, so he was doing some crazy stuff, with his science and everything. And so he didn't want to get thrown in jail either. So he kind of moved to the Netherlands. But anyway, that's neither here nor there. The guy is brilliant. Rene Descartes is. And he came up with the axiom, I guess. I think, therefore I am. The statement, I think, therefore I am. And I've heard that when I was young, and I thought that meant he thought he was like God, like I am. That's what I thought. I wasn't even a Christian yet, but I just thought that's what he meant by that. But as it turns out, it's not. He lived in a time when the scientists were called polymaths. Polymaths were the Renaissance men, basically, the people that did everything. I mean, they did science and philosophy and art and music and all kinds of stuff. That's what these early thinking men were doing, okay, and women. There was a lot of women doing this too. Well, anyway, he came up with that idea because there were some thinking people that said, maybe we're not even here. Maybe we don't exist. And what he said was, I think, therefore I am. And what he meant by that is only a being that could question his own existence, I'm sorry, I messed that up. Only a being that has existence could question his own existence. Makes sense to me. Anyway, Rene Descartes lived slightly before Newton. I mean, I think they think Newton was about 10 when Descartes died. Another guy that I really like, and I mean, if you study him, he's just fascinating. And it's a guy, his name is Gottfried Wilhelm Leibniz. Okay, it's a tough name. Leibniz, anyway, he lived the same time as Newton. I think he was a couple years younger, but I mean, they were contemporaries. They'd gone to high school together if they had high schools. Leibniz was German. Now, Descartes was French, but he did most of his stuff in the Netherlands. Newton was English, did all his stuff in England. Leibniz was German, did all his stuff in Germany. All right. Well, he actually came up with a version of calculus himself, unrelated to, like, independently of Newton at the same time. I mean, the guy was definitely brilliant. Did a lot of work on temperature and things like that. That was what he did a lot of his study on. Okay. But anyway, he also did something that I find to be fascinating. And he argued for the existence of God. Okay. Because there was people back then that said, I don't believe in God or whatever, I guess. And so he argued for the existence of God under a system that he called the principle of sufficient reasoning, okay, or the principle of sufficient reason. The idea is that there's truth, okay, but there's truth that's just true. I mean, it's just true. It's not questionable, and that's called necessary truth. Now, necessary truth would be something like a prime number. Okay, 5 is a prime number. That's it. That's all there is. You can't. It's not a non-prime number. It just is what it is. And if you had 5 marbles in your hand, and you opened up your hand and counted the marbles 1, 2, 3, 4, 5, and then said, there aren't 5 marbles, or these marbles don't add up to a prime number, then you would be doing something called breaking the law of contradiction. Okay, because you can't contradict this prime number and still be right, and it will always be this way. This is a necessary truth. It's necessary. But then there's also something that he called contingent truth. And contingent truth would be something that doesn't have to be, but is still true. An example of contingent truth that I thought of today actually was, I'm doing this podcast. I'm doing the podcast right now, and I don't have to. I didn't have to drive here. I didn't have to bring my equipment here. Oh, by the way, we're here. This is a little different setting. I'm where we do the radio show. Well, you might not know that, but myself and a pastor for the last dozen years do a local radio show where we live. And this is that place. I'm in that studio where we do that. So we're trying that for right now. But anyway, nonetheless, I didn't have to come here. I could have not come here. It's a contingent that I got here, brought my equipment, started this recording, and am now recording it. It's contingent. It's still true. It's every bit as true as a necessary truth. It's just contingent. Okay? So what he said was, the universe exists because we can measure it. We can see what it is. We can we can test it. And by the way, it's repeatable. That's the idea of science anyway. And, you can observe something, repeat it, and that comes into your hypothesis, which comes into your, eventually, a law. Okay? So through the process. But anyway, let's go back. Leibniz said, and he was brilliant. He was considered, he was probably this right there with Newton in his day. He didn't last the test of time as good, but he was considered brilliant. And still to this day, he's considered brilliant by anybody who studies him. But anyway, he just said, we do exist. And is it reasonable to think that something greater, and by the way, that will be part of these laws of thermodynamics, what is the system plus the surroundings is greater than, so 0. But we're going to get into that in a minute. He said, is it reasonable to think that we are here because for no reason, or that something greater than us created us? That was his idea. And he said it was through sufficient reasoning that the contingent truth is that there is a creator. Now, that doesn't prove it's the God of the Bible. He believed in the God of the Bible. He was a Christian. He believed in the God of the Bible and Jesus Christ. But his argument didn't prove that the God of the Bible was this creator. But what he said was, there is a creator of what we have that we can test. And I think that's reasonable. And it's the principle of sufficient reasoning that he came up with. I like it. I like it a lot. So anyway, both Newton and Leibniz worked extensively on something that they knew was important, which was heat. Heat transfers to cold and all that. And Newton actually came up with the law of cooling, Newton's law of cooling. Okay, that leads us eventually to the laws of thermodynamics that we now, have to study in school and use if you're probably an engineer or something. But anyway, nonetheless, it was through the process that they did in the 1600s, or even the 1500s, and the 1600s and the 1700s. Da Vinci all the way through Newton and Leibniz and all those guys, and then into the 1700s, and then even in the 1800s. 1800s where we get it more codified, more written down in equations that we still use right now. Okay, so we get to the 1830s, and we get a guy named, and I'll probably mess people's names up, and I'm sorry, but his name is, I'm reading it because I don't want to mess it up, but I'm going to, Daniel Bernoulli. Okay, he's the first guy that came up with the ideas of molecules, okay, and how they move, and that they move faster in gas than they do in a solid, okay? Now, we'll get into that here in a minute, but that was him. That's Daniel Bernoulli. And then off of his research, a guy named James Joule worked on mechanical relations to electricity and heat, okay? And right now, today, we still have the joule. We call it, that's the power. That's energy. The energy is measured by joules, okay? But it's named after this guy. He didn't name it himself after himself, though, by the way. But it was named after him. Basically, a joule of energy is the energy necessary for 1 Newton to move energy acting on 1 meter of resistance. Okay, and I could have messed that up slightly, but that's the idea. These guys are all smarter than me. By the way, I do not pretend to be smart. I learn because I'm a human, but there's a lot smarter people than me in this world. I'm just telling you what I've learned so far in life. That's all. We get to the 1850s, and we get this guy named Rudolf, once again, Clausius. I'm probably messing up his name. Anyway, Clausius works with William. I can get William right. That's my name, so I can get that one right. And Thomson, that's not too hard. Thomson and Clausius, by the way, William Thomson, he's Lord Kelvin. You may have heard of Lord Kelvin, and if you haven't, you've heard of the Kelvin scale of temperature and all that kind of stuff. Well, that's this guy, all right? Well, he and this other fella, they worked on this idea that eventually gets the first law of thermodynamics, okay? They came up with an equation that it just basically says the delta of energy is equal to heat minus work. And honestly, a lot of the Industrial Revolution came about because of their studies, and this equation right here. They could figure out to build machines to do specific things, plugging in the variables into this equation. So anyway, they came up with this, and they called their energy level the joules. They're the ones that called it that. Okay, the first law of thermodynamics that they came up with, the idea was not new to them, but they put it so that it was, in a nutshell, I guess is probably. But it is the idea that energy cannot be created or destroyed. All right. Now we know that. I mean, I learned that in school. I learned that in probably 5th grade. I don't remember. Real little guy. And it can only be transferred. So what does that mean? Well, I remember as a kid, just as a little guy, before junior high even, we had an experiment where we took ice and we melted it, okay, and then into water. Then we took that water and we put it into a teacup, and then heated up the teacup, the one with the spout and everything, teapot, and then that went into steam. But it's all the same thing. It's all that's the steam is what used to be ice, and what that is the energy hasn't been destroyed. It's just been transferred, but it's got the exact same amount of molecules that it did that the ice had. It's just now different in a different setting. In ice, the molecules are pretty solid. They don't move too much. In fact, the third law of thermodynamics that we will get into eventually state that when it gets all the way to 0 Kelvin, it doesn't move at all. But anyway, in ice, the molecules are still moving around a little. However, they're not moving around a lot. And as it turns into water, you heat that ice up, it gets into water. The molecules are bouncing around a lot freer. And you turn it into a steam, a gas, and the molecules are absolutely flying apart, okay? So, but there's still the same amount of molecules. You've never destroyed or created anything, all right? So, another way somebody showed me one time to illustrate that is everything is in a system. It's either the system or the surroundings. This is first law of thermodynamics, okay? So everything is in a system, the closed system. And for example, this room, we're just going to use this recording studio as a closed system. Everything in this room is part of this system. Everything else outside of it, including Alpha Centauri, I don't care. The furthest star away, I do not care. Everything from the chair right outside the door to, the moon, they're all surrounding this system. And that's what you do. You measure everything off of that system. So you either have the system or the surroundings, and you bring energy into the system, or you exit energy out of the system, but energy's still the same. And so this was illustrated by a balloon. You blew up a balloon with helium, anything that's lighter than air, and it can go up in the air. And so you have this, you tie it off and everything, you put a string on it, and you're holding it, and inside that balloon, inside that latex, is the system now, okay? But it's a system inside this system. The surrounding of this is next step out is this room. But you've got this system with this lighter than air, and you introduce fire. Light a lighter. Well, what's going to happen when that latex melts? And it's going to melt real quick, by the way. It's going to blow up. Bang. Why? Because the gas that's in that balloon that's causing it to rise, that's lighter than air, is going to explode. And when it explodes, it sends those molecules spraying all over the place. Those molecules that were encapsulated inside that balloon are now all through this room. Whoa. Now it's in this system, okay? And yet, if you could measure the amount of energy in this room before the balloon was exploded and after, it would be the exact same amount of energy, just in a different position, basically, for lack of a better term. Anyway, I hope that understands it. Basically, and I'll go over one more time later, the first law of thermodynamics says that everything that is, didn't create itself at all. And no energy's coming in, no energy's going out. We're not creating new energy. Everything is, okay? And then, second law. Now we're going to go to a guy named Ludwig Boltzmann. And I had a teacher named Ludwig in 8th grade, and I absolutely adored her. Man, she was the greatest teacher ever. And I had some really good teachers. I shouldn't say she's the greatest teacher ever, but I liked her a lot. She was a very old lady, too. I don't know why I liked her so much, but man, she just told you the way it was, and I don't know. She's a good teacher, really connected well with kids, especially teenagers, which I was that, a new teenager, like at 13, 14 years old. But anyway, this is not her. This is Ludwig Boltzmann. He lived in the 1800s, and in the 1870s, he came out with the H theorem. Now, the H theorem, I'm going to read it because I already quoted it kind of, but I want to make sure I get it right. Okay. The delta of the system, whatever system, let's call it the universe. The delta of the universe is greater than zero. I spoke that earlier and said we'd get back into it. Well, it also goes and says the delta of the system plus the surroundings is also greater than zero. All right. That's the H theorem. He goes on to explain that entropy to equilibrium will always, over time, get greater. Okay? So entropy will always increase over time in a spontaneous process. Okay, that's important too. The spontaneous process is the process where things are happening naturally, I guess you should say. You can put energy into anything and change it, but everything is going from order to disorder. Everything. And this was illustrated to me by a deck of cards. A deck of cards, you pull it out of the box, and they're in suit and number order. Okay, so you got your ones, or not ones because that's an ace. You got your 2, 3, 4, 5, so on and so forth. And then you have your diamonds and clubs and spades, and everything's in order. Now let's shuffle it up. Let's shuffle it, say, 50 times. What's the likelihood that it's still going to be in perfect suit and number order? Well, it's not going to happen. It will not happen. That is absolutely never going to happen because things go from order to disorder. All right. So Now I know this is. I understand if you're saying like, oh, this, that's not a closed system or whatever. Okay, it works on everything. It really does. In fact, the other illustration that I'm going to use right now is just something all of us know. Let's park your car outside. Just leave it there. Don't drive it. Does your car get faster? Does it get better? Does it get more expensive? Does it, you know, turn the corner better, run a faster time? Does the paint get better and shinier? If left to itself. Remember, this is under a system where everything is just left to the surroundings. Okay, no, it's going to get worse. And in fact, I don't even know if worse is the right way. It's going to become more random. It's going to become more destroyed. Chaos takes place. Well, that fits with the second law of thermodynamics just fine, by the way. But anyway, all that stuff to say that everything goes down. Okay, it goes from order to disorder. That's the second law of thermodynamics. All right, now we got not a whole lot of time left, and so I'm going to go through the third law. Well, here, the third law is actually kind of simple in that it just says that at 0 Kelvin, no more entropy happens. Remember when we talked about ice? Ice molecules don't move too much. Water, they move more. Steam, they move a lot. It's turned into a gas, move a lot. Well, the colder you get, according to laws of thermodynamics, the third law says that at 0 Kelvin, no more entropy will take place. And the no more entropy takes place because, and the reason it does that is because the molecules aren't moving anymore. But 0 Kelvin is really cold. I believe I read it was 273 Celsius. So we're talking negative 273 degrees Celsius, which is like, for Fahrenheit, if we're going to do the math in our heads, it's going to be around 500, I don't know, 525. I'm not sure exactly, but degrees Fahrenheit below zero. So it's really cold to cause things, to molecules to no longer move. Okay. Now that is what the law says there. So that's the third law. There is a fourth law. It's kind of the transitive property. It just says basically if this item is this cold and this item is this cold, and then a third item is as cold as the second item, then the third item is the same temperature, just as cold as the first item. You might remember that from math in school. A equals B, B equals C, therefore A equals C. It's just the transitive properties. But why is this even important? Why is the study of thermodynamics even important? Well, you know that without these studies, we wouldn't have quantum physics or quantum mechanics at all. No, none of that yet, because Einstein is the one that came up with, the theory of relativity, came up with the special theory of relativity. He did that, I think, in 1905, I think. But while he was studying the laws of thermodynamics, especially the second law, okay, that's what he was grappling with, and all the implications with that. And he realized, of course, we have depth, height, and breadth. We have the 3 dimensions that we live in and everything. Well, he took, to make all the math work, and he put in the dimension of time, energy equals mass times speed of light squared, that kind of stuff. And he took it to the next level. And then, of course, he actually realized he was incorrect on some of his stuff because he believed in a steady state universe at that time. I think everybody did. But through the next short period of time, they kind of figured that wasn't true, and it's not a steady state universe. The universe is expanding, and as it expands, eventually it will contract and all this other stuff. So he put that into the equation. That's the general theory of relativity, and that's the one that we all accept. That's the one that physicists. That's the reason we get Einstein awards. That's why we call smart people Einstein, because of that. That what he figured out. But he did that while he was studying this. And by the way, we can measure stuff. We can, and it's the craziest things. I know I'm no brilliant guy. I'm not, but I love studying this stuff, and you can measure things and everything. Do you know that things can get so small that they can't be anymore? And I think that's according to quantum physicists. That's a negative 30 to the negative 35 centimeter, 10 to the negative 35 centimeter, I think it is. At that point, whatever it is ceases to exist in one place and is apparently permeable across the whole universe. I don't get it. And by the way, it doesn't hurt my feelings. I don't understand it, because there was a guy named Richard Feynman. He's one of the most brilliant people of the 20th century ever. There's nobody going to argue with that. Richard Feynman's top-notch brain guy. And he said, he was a quantum guy. And he actually said, if you think you understand quantum mechanics, you don't understand quantum mechanics. So I'm in good company with that, because I don't understand it at all. But I certainly like reading about it. But anyway, back to what I was saying. Why is this even important? Well, this is it. And this is for the whole reason for this study as we're studying the Bible. Genesis 1:31 says, God finished creating everything on day 6. Now, what does that mean? I don't know. Okay, I'm not a young earther or old earther. I'm not any of that stuff. I'm going to let God work it out. I actually read a physicist actually that did something with the expansion of the universe, where he said, because it is true, according to Einstein and everything, that the speed you're traveling changes time. Okay, and he said that at the expansion rate of the universe, if you were standing on the outside, it's been about 6 or 7 days. If you're standing in the middle, it's been billions of years if you aren't moving. And kind of makes sense for quantum physics, I guess, but I don't understand quantum physics, as I just said. Neither does anybody else, as Richard Feynman says. But anyway, I don't understand all that. But the Bible clearly says that God stopped creating. Okay? That ended bringing in energy to this universe on day 6. First law of thermodynamics. Done. 2 Peter 3:10 says that all things are running down. Everything is going down, going from heat to cold, going to the ambient. It's going to be over with someday. Now, he doesn't use those terms, but he does say this whole place is going to be, it's going downhill, downhill, downhill. It's not getting better. It's getting worse. I know we all, since, Darwin, we all say everything's getting better, but I don't know. I'm dubious myself. But anyway, nonetheless, I'm just making a joke. But Peter tells us that everything's going downhill. Second law of thermodynamics. It's exactly what we see. Third law of thermodynamics, it says that everything's going to go to the ambient, to the cold, to Kelvin, 0 Kelvin. Well, in Isaiah 34:4, it's very interesting. Isaiah lived 700 years before Christ. So 2,700 years ago, God tells him something. He's a prophet, and I guarantee you he didn't understand this. I don't understand this, and I live now, but it fits. It says, look it up for yourself, but Isaiah 34:4 says that God was going to roll this universe up like a scroll and be done with it. Okay? And he's going to do something new. Now, I believe that, and that book of Revelation tells us that. Daniel tells us all these things. Prophets tell us that. I believe that's true. I don't know when it's going to happen. You're never going to hear me talk about the date that Jesus is coming back. I believe he's coming back. I don't know when. Could be with my grandkids. Could be my great-grandkids. Might be tomorrow. I ain't got a clue. But that's the third law. So these fit. First, second, third law of thermodynamics is what we should find if we're reading our Bible and we believe what it says about this universe and where it came from and where it's going. All right. And then that Daniel Bernoulli guy comes to mind too. He's the one that found all the molecules. In Hebrews 11:3, it says, what we see are made up from what we cannot see. Everything that you see is made up from what you cannot see. Hebrews 11:3. These are crazy statements back before anybody could know a lot of this stuff. But God knew the whole time. He told some of his people. They wrote it down. We can now read it. I think it's reasonable to believe in God. I think it's reasonable to believe the Bible. I think that Leibniz had it right with that. If something's reasonable, pay attention to it. So anyway, thank you for joining us on, and this is it. Thank you for joining us in every Tuesday. I hope that we're going to be dropping a new one, and I hope you tune in. And we are now 10:10 for this edition, and I hope you join us again. Thank you.